Okay, welcome back. Uh, so today we're gonna continue working on chapter five of the intro of number theory. Last time we ended up and I believe it was almost like the last problem. Actually, it's second to the last. Well, you in fact, if we actually want to um if we are going to pay attention to the last problem of this chapter, it's actually a problem of writing a program for the algorithm 3 plus 1. Um, and Again, it is, of course, considered as part of the um, the math subject. However, it is more like a relying on the technology that we can have in order to do the math problem. So for such kind of problem, which is kind of like as well as the problems that ask us to write like a paragraph or like a like a one to two page paper to we're going to skip those because again it is better to try focus on. So today we have one problem left. So ideally, we'll be able to finish it. And also, first, I need to apologize for what happened in last week. That the first hour of the live, there was a technical issue that I didn't aware of. So we kind of did it without any with only the audio, but couldn't see uh mm, the actual the actual problems that we're working on. So if we have spare time today, hopefully we finish this chapter. If we have spare time, we might probably just go back to those problems and see and try to quickly go over the solutions. Okay. So last week we ended up in the second to last problem, which is a 3 plus 1 algorithm, also known as the Collat's conjecture. And then we're gonna play around with the idea of it. And once again, this conjecture is not proven yet. Where the conjecture itself says that using this algorithm, 3 plus 1 algorithm, uh, all natural numbers, in other words, all positive integers, will always end up with always end up at 1 4 2 1 loop. Okay, in other words, the 4 to 1 loop will be the only solution or the only loop when we try whenever we try to pick a number and play around with the algorithm. Now, this conjecture is still open, meaning that there's no proof or disprove. It's not proven or disproven. There's no an actual proof that this concept or conjecture works for every natural number or any positive integers. But of course, with the help of technologies like coding, mathematicians have already proven. Um, I believe it was like a number up to like three times, like 10 to the like 17th or 20th power. That's for all numbers less than or equal to that. These number if we start with these numbers, it will eventually hits 4 to 1 loop if we play the algorithm. So this of course does not mean that it is always true, because again in math and logic, having large amount of examples does not mean that the statement is always true, because In order to make it false, we just need one single counter example. No matter how many examples that makes it work, does not mean that there does not mean that we cannot find a counter example or an example that fails it. And of course, if we can find a number that fails it, of course we can disprove the conjecture. How and again, unfortunately, until now, this conjecture is not been proven because we couldn't find a counterexample that makes it fail. So anyway, we're gonna play around with this algorithm and start with something very easy. So last time we ended at this part. Um, Problem A. Find the length and terminating value of the 3n plus 1 algorithm for each of the following starting value of n. And then we're at the third one when n is equal to 31. And somehow we actually kind of see a loop there, which which is actually incorrect, obviously, because it's been proven again by a lot of mathematicians that this loop we couldn't find any loop first of all, and then at least it will be true for small for some small value, especially small value like in 2 digits, it will not work. Now where did I make a mistake? I actually made a mistake when I ended at 310. Okay. Once again, this algorithm says if you have a number, if you have the integer is even, we have it. If it is odd, then we're going to multiply by 3, then add 1. Now, here is the reason why we actually got a loop here, because we actually made a mistake on our division. So this sequence looks too long. I'm going to separate into several lines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to put this here. I'm going to separate the sequence into 10, 10 terms per line, so that it's easier to keep track on our accounting, as well as seeing the mistakes. So starting from here, when we have 310, of course we're supposed to divide by 2. But if we divide 310 by 2, we actually don't get 165. Okay, again, 165 times 2 is not 310, it's actually 330. And that's where I made a mistake. And then it looks like that I'll actually hit back 31, which actually kind of creates the loop that we see. Okay, so what would the correct answer be? Well, it'll be 310 divided by 2, which is actually 155. So now we see that 155 actually has not appeared in this sequence. So it means that we don't have any loop yet, which is what we expect. So 155 is an odd number. By the algorithm, we need to now multiply by 3 and then add 1. Multiply by 3 to get it will give us 465. Plus 1 will get 466. Now, of course, we get an even number. We have it, 233. And then there's an odd. Multiply by 3, we get 699 plus 1, which is 700. So 700 is an even number. We have it, 350. Have it again, 175. And then if we keep going, we have 175 as an odd number. Multiplied by 3, that is going to give us 525. And then plus 1, we get 526. And then if we get an even number again, so we're going to have it. And so far, we still don't see any number that has been repeated in our sequence, which again is supposed to be what we expect. So great, we didn't make any mistakes so far, technically. So anyway, if we keep going, we get multiply by 3, 789 plus 1, which is 790. So then if we get an even number, we have it, we get 395. Then once again, we're going to multiply by 3. Um, this is going to give us, let's see, 395 is 400 minus 5. So it's going to be 1200 minus 15. So it's 1185 plus 1. Yeah, don't forget the plus 1. It's actually very important. Otherwise, we'll never actually have the number. Okay, so we get an even number. We have it. We get 593. Okay, so odd multiplied by 3 and then add 1. So that's 600 minus 7. So that's 1800 minus 0.1. So that is going to give us 1779. So we now can have it. Having we get 890, and then it's even. We have it again for 45. So we triple it. We get let's see, that's 450 minus 5. So 1350 minus 15. So 1335 plus 1 is 1336. And again, we have an even number. We can now have it. And surprisingly, we pick a number 31, and then we already have more than 31 numbers in our sequence before before it terminates. Okay, which actually happens sometimes in this. We're going to have it again, so we get 334. Let's even have it one more time to get 167. And still, we do not see any number that has been repeated so far. So let's refresh it, and then we're going to get, well, 167 is odd. We're going to multiply by 3, which gives us 501. And then plus 1, we get 502. And then after that, we have it. We get 251. And then we have to triple it to get 753 plus 1 is 754. And then if we keep playing this game, we actually will get something that looks like it never ends, right? So in fact, it didn't really mention in this how should I say it? If you go back to the problem itself, it says actually there should be 2 possibilities will occur. Actually, there's one more that did not really mention. Well, the first one says we'll end up repeating some number A that appears earlier in our list, which is again seeing a loop. And then number 2, we may never repeat the same number, in which case we say that the algorithm does not terminate. Okay, so we can imagine that what we really want to say is that in the actual conjecture, we assume that all numbers will actually get down to 1, and then of course starting from 1 we actually see the loop 421 loop. Okay, then and once again this is what the conjecture is assuming. Of course, we can also prove it wrong, but actually in two other ways. Suppose that we actually can get a different loop other than 421. So in other words, there could be a way that makes the conjecture fail, which is there exists a different loop other than 421 loop. Meaning that there could be a loop such as, let's pick a number, pretend that it's going to be a loop. Let's say it's the 31 that we have. And then somehow, like if we play the algorithm, it comes back with 31. Then we will say that this creates a loop that you will eventually get 31 again and 31 again, so on and so forth. Meaning that this loop will be different from the 421 loop, and we'll never be able to get out from it and get the sequence all the way back down to 421. Okay, so that is one way. There's one possible outcome other than the conjecture. Like one possible outcome that makes it fail, and then the other possible outcome is in fact the one that mentioned down here. We may never repeat the same number, in which case we say the algorithm does not terminate. But if we think deeply, because natural numbers um, are, of course, unbound, the number of natural numbers are unbounded, meaning that natural numbers there are infinitely many natural numbers. You can if no matter what natural number we name, there's always one bigger than it, right? So if this algorithm does not terminate, the only way to make it work is that we can always get some natural number bigger at some point in the sequence, and then it'll frequently appear like that, meaning that we have to have we in this sequence we have to have uh the natural numbers are getting bigger and bigger and bigger, because if there's a final uh step that makes it bigger, and then after that all the numbers are getting smaller and smaller, eventually it will get down to one again, meaning that we will actually be able to terminating it. Then it will actually be different from what we expect here. So in order to say that it will never terminate, the only way to make it work is actually growing bigger and bigger. So at some point, okay. Now this actually we don't know whether it's gonna happen or not. But in our example in this problem for 31, it looks like that it's kind of like it will never end. The number is getting bigger and bigger at you know at at every other moment. So we're going to see what's going to happen. So if we keep going, 30 and 377 is odd. Multiplied by 3, we get 1131. And then we're going to add 1, so we get 1132. Now we get an even number. See, once again, wherever we hit an odd number, we are supposed to assume that it's going to grow bigger, because when we hit an odd number by the algorithm, we're going to multiply by 3, which is multiplying a positive number by scaling it 3 times. Of course it gets bigger, and then we also have a plus 1 after that. Okay, then in this case we have 1132, which actually gets bigger, which kind of looks like the second the second possibility that actually being occurred. But again, now it guarantees us to get an even number, so we have to have it again. So we now get 566, which is even. So we still need to have it one more time, and then we get 283. And once again, we hit an odd. We need to multiply by 3, which gives us 849 plus 1 to get 850. Now we get an even. We have it. We have we have 425. Now we have an odd. We have to multiply by 3 to get 1275 plus 1, which is 1276. So let's see how many we have here. 3, 6, 3, okay, 10. So let's move on to the next row. So now we actually get an even. We need half it again. So half it will give us 683. Then we have even. We need to have one more time to get 319. Now we have odd. Multiply by 3, so we have 957 plus 1 is 958. Even, we need to have it again. So, of course, the best way of doing this kind of problem is actually trying to trying to use a computer to write an algorithm like the last problem of this chapter, and trying to run it to make it faster. But if you don't have you don't have you don't have any program for coding, or any calculator like I do, well, it's gonna get boring, because it's so repetitive, like what I'm doing. But yeah, we still try to figure out what the results will look like, and see if it actually matches our assumption. So we have odd multiplied by 3, we get 141. Let's see, 141, 140, 1437. So we get 1438. Then we have even, so we're going to have it 719. So it's odd. We need to multiply by 3, 2157. So it will be 2158. And then we're going to have it to get 1079. So multiply by 3, we get 3237 plus 1, so it will be 3238. And then we have it again, we get 1619. So I think we actually hit 10 again. Right. So now we have to move on to the next row. Multiply by 3 to get 4857. Then times 3. I mean, that's multiplied by 3 plus 1, which is this. And then we have it. We have 2429. Now we multiply it by 3. We get 72. What is it? 7287 plus 1, which turns to 7288. It looks like the number is growing bigger and bigger, like the second case. But now, if we pay attention, here is the magic part. We got an even number, of course. We need to have it. So if we have it, we get 72 turns to 36, and then we get 34 and 44. Now we still have an even number, meaning that we need to have it again to get this. And this is also even, so we are going to have it again to get 911. So all of a sudden, we actually got from over 7,000 all the way down to less than 1,000. So sometimes this happens, even though we actually have been growing and growing, uh, uh, like slowly in the sequence. At some point, if we have something like multiple of 8 or multiple of 8 or 16 like that, then we actually will make the number a lot smaller all of a sudden. So this is the reason why it is very hard to predict whether or not like it's possible to find a number so that the sequence after all will continue forever without terminating. So if we keep going, we get 2734, and then we have it. We get 1367. Then next we have to triple it to get let's see 201, and then 39, so 4001 plus 1 is 402. Then we have 1 2 3. We can put one more number. We have it. We got 201. Great. Then after that, we multiply by 3 to get 603 plus 1 is 604. Now we see that this number is, once again, multiple of 4, which actually will reduce it down this even number all the way down to an odd number, which is smaller than the previous odd number. Okay, so if we do that, we get 3002, and then we have it again. We get 1501. Now, this is one of the keys of studying this algorithm, because if we try to focus on the even numbers, we know that the even numbers will always reduce down to some odd number at some point. Okay, then what we actually need to worry about is the change in the odd number parts. Okay, because we know that once like the odd number will definitely will actually follow by well, it's actually following by an even number, where the even numbers will actually got reduced down to an odd number once again. And then that odd number will actually get back into an even number, and then it goes back down as an odd number. So we actually can see the growth are kind of like a kind of like a like kind of like a wave shape. Okay, so it is, in fact, it's actually easier to focus on just on the odd number part if you actually want to study like all those sequences and see and it will be easier to see whether or not this sequence is gonna terminate or getting a loop. Okay, So now we have an odd number, so we need to multiply by 3 and then add 1. And once again, the good part of stealing 0, 1 is this by 3, and then add 1, 4 to 1 loop. And because this is actually very important. With this part, if we can actually get control, everything down to like the 4 to 1 loop, we can actually get the decay a lot faster. So once again, we see this, we will have to have it because it's an even number. So if we have it, we get 2252. And 2252 is definitely an even number, so we can have it one more time. Meaning that we actually, after we multiply by the odd number by 3 and then add 1, we actually have it twice already. Meaning that we actually divide that by, that new number, that even number, by 4, which actually will definitely get smaller than the previous odd number for sure. Um, So in that case, we get 1126, and luckily we got an even number again. We can actually have it. And so far, we still don't see any number being repeated, which is what we expect. So we're actually in a good shape. So we have 563. Now we actually had an odd number. We need to multiply by 3 again, which is let's see, 56 times let's see, we end up with a 9 at the end, and then 56 times 3 is 168. So we need to add 1 to get 190. Okay, 90. So we have even number, we have it. Then we have odd number again. We need to multiply by 3 and then add 1. So we have 135, 2535 plus 1, which is 6. And now with an even number, we can halve again to get 1, 2, what is it? Let's see, 1, we have a 6 here, and then we have an 8 here. And now we have an even number again. We can have it one more time to get 634, and then we have even. We can have it once more, 317. Now we had an odd. We need to go back, multiply by 3, which gives us 951, and then plus 1, which is 952. Now, once again, we actually hit an even number. And in fact, it's a multiple of 4 if you remember how to do, the trick of identifying integer or positive integers. We can quickly realize that it's a multiple of 4. So we will expect to actually get reduced down, by 1/4 of it at least, so that this number is going to be smaller than than the previous odd number 317. So if we do that, we get 476, which is again even. So we can have it again to get through 238, and luckily this is also even, so we can have it to 119. Okay. Now 119 is odd. We need to multiply by 3 to get 357 plus 1, which is 358. So again, we still don't see any number that has been repeated in this sequence yet, which is a good thing because now we don't see any loop. Okay. So we continue. We have to have it to get 179, and then 179, right, that's correct. And of course, we didn't see 179 in our sequence yet. Then after that, we have to multiply by 3 because it's an odd number. So we get 537 and then plus 1, which is 538. Great. Then we can have it to get 279. And then it's an odd, so multiply by 3, 78. Actually, we get 807 plus 1 is 808. And clearly, this is a multiple of 8. We all can figure out easily. Have it to get this, have it to get this, have it to get 101. And see, we finally drop back down to like around 100. Of course, this is not done yet because we didn't see any loop yet. And of course, when we say the loop, we expect so far the only loop that we know of is the 421 loop. So if we see the one, we know that it's gonna start it's gonna terminate at the one because it'll get back to a loop afterwards. Now with this, we have to multiply by 3 to get 303 plus 1, which is 304. And once again, it's an even number, so we can have it. And then this is still even. We have it again to get 76. It's still even. We actually see that we can have it 2 more times. 38. So let's see, 369, right. And have it one more time to get 19. So finally, we get a number that is smaller than what we start off. So if we pay attention, we actually can see that so far we started off from 31, and then for the entire sequence that we actually have all the numbers are bigger than 31, which actually could happen in this algorithm. And but that does not mean that it will never terminate. It will grow up forever. Now we finally see the first number that is smaller than what we started off, and this is the reason why this proof is actually very well. This conjecture is very hard to tell whether it's true or not. So with 19, we're going to multiply by 3, which is 57, and then plus 1 to get 58. And then after that, have it to get 29, multiply by 3, 87, and then plus 1, which is 88. And now again, we see that as a multiple of 8. We actually can have it 3 times to get down to 11. Now, do we actually get 11 above? Not yet. So imagine you do our calculation, do the calculation on our own. So in this case, we need to multiply by 3 to get 33 plus 1, which is 34. And then we have it to get 17, and then multiply by 3 to get 51 plus 1, which is 52. And therefore, now we can actually have it twice to get 26, and then 13. And we finally hit something that we have seen in the previous 2 parts. We have 13, which we know is going to end with 1. We get 40, 20, 10, 5, 16, 8, 4, 2, and 1. And there we go. Meaning that this length is not is of course not simply just 10. It's very long. We know each row has 10 terms, including the last row. Let's count how many rows we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rows, meaning that the length is 12 times 10, which is 120 in this problem. And of course, the terminating value is, of course, not 31. It's going to be 1 here. And there we go. And this is an example of picking a starting number with the length that is that is bigger than the number itself. In fact, we actually see that this number, this length, the length of the algorithm is actually is almost 4 times of the number that we picked. So finally, we finished problem part A. We're going to move on to part B. Part B says do some further experimentation and try to decide whether the 3n plus 1 algorithm always terminates, and if so, at what values it terminates. So we actually we're not going to do any we're not going to do any further examples here, but we can just simply answer it. So based on our based on our observation, we can actually assume that um, it. I'm going to do quote to quote. Okay, looks. Oops, wrong code. Looks like it. Well, I should just write out the 3+1 algorithm always terminates at 1. So once again, why do I put quote unquote looks like? Because this is a conjecture that has not been proven or disproven yet. But based on the observations that mathematicians have about this conjecture, for for the finite amount of values that they pick up to, I believe it was is still 3 times 10 to the 20th power. I don't remember, like the exponent part. Like for all those numbers below that, they all will terminate at 1, meaning that they all will actually end up with the loop 421. Okay, so part C, assuming that the algorithm terminates at 1, which we kind of assumed, um, let L of n be the length of the algorithm for starting value n. Okay, for example, L of 5 is equal to 6. Well, we can check it. 5, if we start with 5, we the next number is going to be 3 times 5 plus 1, which is 16, and then we will halve it to 8, halve it to 4, halve it to 2, and then eventually have it to 1, and we know that it terminates at 1. So in this case, we actually get exactly 6 numbers or 6 terms in our algorithm or in our sequence. Okay, and then another example is L of 7. Length of 7 is equal to 17. And again, we start with 17. We actually will, the next number is going to be 22, 11, 34, 17, 52, 26, 13, and then 40, 20, 10, 5, and then we're going to get back to what we see. Starting from 5, we'll just add 5 more there. Okay, 16, 8, 4, 2, 1. That's exactly 17. Okay, so what is this question trying to ask? Show that if n equals k 8k plus 4, with k is strictly greater than 1, then L of n is equal to L of n plus 1. Hint, what does the algorithm do to the starting number, to the starting value 8k plus 4 and 8k plus 5? Okay, so let's see what's going to happen. Okay, we're going to now do some calculations and also like do some proofs. So how does it work? Well, let's see. Here comes the proof. Okay, so we are going to consider uh, we're going to consider ln instead of considering the ln part, we're going to consider the sequence of when we start off with and n plus 1. Okay, consider the sequence starting well starting from, of course, n equals 8k plus 4. And then we're going to see what happens if we start with 8k plus 5. Then the sequence would become, now of course we are going to look at the sequence itself and see what's going on. So starting off with 8k plus 4 with, of course, it says k is strictly greater than 1. Okay, then the first number is the n value we start off, and then next we're going to get uh, we're going to get half of it because clearly it's an even number. And clearly this is also an even number, so we'll have it one more time. Then we hit an odd number for sure because k is an integer times 2, meaning that it's an even number, plus 1 turning back to an odd number. So multiply by 3, we get 6k plus 3, and then don't forget to add one more to get this. So that now we have an even number again. We need to have it. Now here we don't know if it's odd or even for now. So I'm going to pause right here. I'm going to use L dot to make sure that it still continues at some it still continues. The sequence continues. Now, why does this matter? Because at this point, uh, we still want to see where it starts having the same values in the sequence. Because once we actually get the same value between the two different starting number, that means everything afterwards will be the same. Just like in our first example here, when you do 31 at the end, we eventually hit 13 in the last row. But once we hit 13, we know the rest of the sequence will be the same as the sequence of 13 itself. So, in other words, if we see there's a number matching two sequences, then everything afterwards will also be the same. Okay. So for the first sequence with n equals ak plus 4, then we have the sequence for first 5 terms of the sequence. We actually see these 5, okay, where the sequence starting from n plus 1, which is again becomes ak plus 5. Well, we still have with k is greater than 1 as our condition, which is, that's given. We don't know what's going to happen. The sequence would become, now we're going to see what happened if we start with 8k plus 5. So if we have 8k plus 5, we already know that it starts off with an even number, or with an odd number, excuse me. K is an integer times 8, which is multiple of 8, of course, is even, plus 5, which is odd, so we end up with odd number. So our first step would be multiply it by, what is it? Multiply by 3 to get 24k plus 15. And then don't forget to add 1 to get 16. Therefore, we see that this is a multiple of 8, right? So we actually will get, if we can have it, to get 12k plus 8. And then if we have it again, we get 6k plus 4. And of course, we'll end up with 3k plus 2, and then we have the rest. So notice that between the two sequences, only the first 3 terms are different. Starting from the 4th term, the sequences become, well, you can think it like identical, technically, meaning that if we ignore the first 3 terms, starting from the 4th term, the 4th term actually follows, and then there's nothing extra, nothing missing. Becomes identical to each other. or to, yeah, we can say to each other. So we can conclude that therefore the two sequences have the same length, i.e., what did they use? The length of n is equal to the length of n plus 1. Not capital N, by the way. Otherwise, it will consider as different n's. So this will be our proof for uh, part C. Great. So now we have part D and part E remaining. So show that if n is equal to this value, then we have this and this. So part D is an extended problem from part C. Okay, we can of course we see that. So we're still proving it. So let's start with again proof. Then we're going to see how to prove it. Uh, so notice that 128k plus 28 is in fact equal to, I'm going to use a different letter, okay? Which is actually equal to 8 times 16k plus, we want to have a 4 outside, right? How do we get the 4? That is, we actually have 4 times 7, but in fact, we can break it into 4 plus 24, where the 24 can be actually combined with the 8 here. So we see that, and for, of course, k is greater than or equal to 1. Okay. And notice that even if we include k equals 1 here, this part, the 16k plus 3 will be strictly greater than the initial k that we have in the previous problem, meaning that everything inside of the parentheses will always be greater than 1. So it actually satisfies that. So this satisfies the previous part, which says n is equal to L of n plus 1. Hence, it is sufficient to show that, I'll say, let's pick Ln and Ln plus 2. Okay. Now, why would I choose that? I don't know either. Maybe n plus 1 would be a better option, but who knows? Let's give it a try, see what's going to happen. Okay. So far, this is actually, we're using the answer from the previous part to shorten our proof, and also trying to save our time, make it not too redundant. Okay. So here we go. For n equals, well, we can say like for the sequence starting with n, we obtain, or we get, doesn't matter, again, wording, as long as you don't use the wrong wording, is fine, as long as they understand what's going on. Okay. Now, of course, n, what's n again? It is actually equal to 128k plus 28. Okay. So if we do that, we will start off with 128k plus 28. Then it's a multiple of 2. We can have it to get 64k plus 14. Then we have it one more time. we get 32k plus what is it, plus 7. And now we actually hit an odd number, so we need to multiply this by 3 to get and then add 1 to get this, and then we are going to have it one more time, 48k plus 11. And once again, this is guaranteed to be an odd number because we have 48k as an even number plus 11, so it has to be odd. Multiply by 3, we get 144k plus 11, then add 1 becomes 34. I mean, 11 times 3, add 1, okay? And then after that, we have it one more time. We get 17, and then we need to triple it again. 220. Is it 228? No. That's 4 times. 216k plus 17, which gives us multiplied by 3 is 51 times 2 plus 1, 52. 3, 4, 5, 6, 7, 8. So let's do 8 numbers in one row then. Then we get half of it, so it's 108k plus 26. And this is clear even, so we have it one more time to get 54k plus 13. And this is absolutely odd, so we need to multiply by 3 and then add 1 to get 40 here, and then have it. We now get something that is that's inconclusive, because now we don't know whether 81k is an odd or even number, because we don't know whether k is odd or even. So after this, we cannot tell what the next one is, but we know that this sequence is not over, because our assumption is it will actually get all the way down to 1. And here we have 81k plus 20, where k is a natural number. Clearly it will be bigger than or equal to 81 plus 20. This definitely is absolutely greater than 1. So we have to we have to continue the sequence. So now we're going to pick, and for the sequence starting with, well, we say we're going to pick n plus 2. So in this case, we will use, we actually will obtain starting with n plus 2, which is 128k plus 30. Now I can guarantee that there will be a lot of numbers we need to get before we don't know before we get to a number that is inconclusive of what our next step is. So here we get definitely an even number. We have it. And now we actually hit an odd number. So what do we need to do? Well, we have to multiply by 3 and then add 1. So we have 45 plus 146. Then we're going to have it one more time to get this, which is even. Now we get to we have to multiply by 3 again, and then add 1. 1, 2, 3, 4, 5. We actually need to do a few more. So we get even number. We have it again, 35. And then we get an odd number. We need to multiply by 3 for 32k plus now 35 times 3 is 105 plus 1 is 106. Then how many do we have? 2, 4, 6. I can put one more number. So we get even number. We have it. If we have it, we get to 16k plus 53. Of course, it's still not done yet. This is clearly an odd number. Multiplied by 3, we are going to get 648k plus what is it? 130, 160, no, 159 plus 1, which is 160. Then after that, we're going to we get even number. We're going to have it 324k plus 80, and then even again, we are going to have it. Uh, let's see. What do we have? 230, well, 324k plus 80. We have it. We get 162k plus 40. Then if we have it one more time, we get 81k plus 20. And then again, now we get something that is inconclusive. And we now hit again 162k plus 40 and 81k plus 20. So lower dots like this. And once again, our what is it called? Our conclusion is that notice that between the two sequences, only the first, let's see, we have one row which is 8, and then 9, 10. Let's see, two more terms in the second row, two more terms in the second row. So we actually see that only the first 10 terms are different. Starting from the 11th term, the sequences become different. Therefore, the two sequences have the same name, and then i.e. this is this. So now we can conclude that thus is equal to n plus 1, which is actually from the previous part, which is equal to L of n plus 2 from this part. So we finally finished everything. All right. Last but not least, okay, this is a little bit too long. I'm going to fix it. We have this with this with this. Let's see. I'm going to let's get the 1, 2, 3, 4, 5. Let's do 5 instead. So this is what we're going to do. Here we go. Let's shorten a little bit. And then let's see. 1, 2, 3, 4, 5. Here is where we should break into the second row. And here comes the third row. Okay. Now it should look better. We will be able to fit in. Excellent. So we actually see that each row has 5 numbers, technically 5 numbers. Okay, and then we will be able to conclude that the first 2 rows, okay, which are the first 10 terms, are different. Starting from the 11th term, which is the first term in the third row, it actually get repeated. Okay, so last but not least, we have part E. Find some other conditions similar to those C and D for which consecutive values of n have the same length. It might be helpful beginning by using the next exercise to accumulate some data. And again, this is actually this is actually quite hard because once again, we need to make a program in order to do it. So, in fact, let's try to skip it. Okay, if you're interested of the idea of collage conjecture and want to play around with it, I'll definitely recommend you to try to work on problem 6. Especially if you're very good at programming, making a math program to actually run an algorithm. and then try to play around and see if you can actually find find any conditions or any interest moment in this algorithm. Okay, all right, then let's go back to, I don't know, where did I actually not go through last time. Okay, so I believe we already did part problem one. So let's see. Prompt two once again is a program thingy. So I think last time I started off at problem three, which asks us um to play around with the um wait, hold on, am I on the right track? Yeah, I'm on the right track. The Euclidean algorithm, and then trying to prove something. Okay, so uh uh, I've already run out of time, so let's call it this the end. If I have time at some point of this week, I'll try to make another live stream to go back to problems 3 and 4 in this chapter, um, and trying to talk about the solutions of those problems with the actual actual words here, so that you guys can not just only hearing it but seeing it, how it actually goes. And then after that, from next Thursday, we're going to move on to chapter 6, which is linear equations and the greatest common divisor. And we're going to start a new chapter and work on the problems in that chapter. All right. Thank you, everyone, for watching. I'll see you next time.